Good morning students and welcome to my channel, that is Easy Chemistry by SBG. Today we'll start the chapter number 2nd, it is IR spectroscopy. IR stand for infrared. Infrared spectroscopy we have to study in the details. Infrared spectroscopy is one of the most widely used tools for the investigation of structure of unknown organic compound, where in the IR spectrum of an organic compound provides the information about the functional group present, specifically the functional group present in an organic compound. The spectrum is obtained within 3 to 7 minutes time required to get the spectra. In IR spectroscopy, time required is very short, that is 3 to 7 minutes, and very small amount of sample is required, that is 4 to 5 milligram sample is required for the IR spectroscopy. So first, what is the electromagnetic radiation? Electromagnetic radiation is a ray of light. That ray is composed of a different wavelength. That ray is composed of the different wavelength. If we see from the source of light, the rays comes out. First ray which having the maximum energy and shortest wavelength, that is the cosmic ray, and the second one is the gamma ray, third one is the X-ray, then UV, visible, IR, microwave, radio, and last one a TV. So if we see the wave from the incoming from the source, then the wavelength is very short. Likewise, then in progress wavelength is increases from cosmic to the TV. So likewise wavelength is goes on increasing and energy is decreases. Energy decreases. If we see the wavelength is denoted by the lambda, and it is a length, so it may measure in the meter, nanometer, angstrom, depends on the value. So cosmic ray having the very short wavelength. After the cosmic ray, the gamma ray, is below the gamma ray. Range of the gamma ray is 0.2 angstrom, 0.221 angstrom is the range of gamma ray, and below the 0.2 angstrom is the cosmic ray. Then X-ray ranges 1 to 10 angstrom, 1 to 10 angstrom X-ray. Then UV range is from 10 to 4000 angstrom, 10 to 4000 angstrom. Then visible is ranges from the 4000 to 8000 angstrom wavelength. Then IR ranges from 0.5 micron to 200 micron, the region of IR. Then microwave ranges from 1 mm to 10 centimeter. Then radio wave 10 raised to 9 to 10 raised to 14 angstrom, and below that this is TV radiation. So this is a wavelength given for the radiation. Unit of wavelength is either angstrom, nanometer, micron, centimeter, or meter we use according to our convenience. As we see, the energy is more here. Energy of the cosmic ray is very high as compared to the gamma and then X-ray. So energy is high near to the source, and frequency is directly proportional to the energy. So frequency is also high. Frequency is also high, and again wave number is also high. Wave number, because frequency and wave number is proportional. So the energy, frequency and wave number is higher for the cosmic ray, while the lowest for the TV, radio and TV radiations. If we talk about the wavelength, then wavelength is increases here. Wavelength is increases from cosmic ray to TV ray, and the wavelength and energy is inversely proportional, as we see later on. Let us see the infrared radiation. The infrared radiation, as we know, it ranges from infrared radiation, its wavelength is from 0.5 micron to 200 micron. Then this region is further divided into the three regions, that is near IR. First region is called as the near IR. Second one, middle region, is the ordinary IR. Ordinary IR. And third is a far IR. So near IR and ordinary IR, it ranges from 0.5 to 2.5 micron. Then 2.5 to 15 micron is the ordinary IR, and 15 micron to 200 micron, it is a far IR region. Further, the ordinary IR is divided into the three groups or three regions. So first region is functional group region. Functional group region. Second region is fingerprint region. Fingerprint region. And third one is aromatic region. Aromatic region. So the range for this region is for functional group region, it ranges from 2.5 micron to 7.7 micron, and from 7.7 to 11 micron is the fingerprint region, and from 11 micron to 15 micron it is the aromatic region. So this region gives idea about the spectrum obtained in this region, gives idea about the kind of structure present. For example, if we get the spectra in between the 2.5 micron to 7.7 micron, then it indicates the presence, this spectra indicates the functional group. Then fingerprint region indicates the exact match, means if we have any structure and if unknown compound matches the spectra of the known compound, then we can compare the structures. Then aromatic region, we will get the stretching frequency band at the aromatic compound for the aromatic compound in aromatic region. But generally we calculate the we prefer the unit instead of the wavelength. We use the unit as a wave number, means the unit of wave number is a per centimeter. So in case of the per centimeter value, the functional group region lies in between 4000 to 1300 per centimeter wave number, while the fingerprint region it lies in between 1300 to 909 per centimeter wave number, and third one is aromatic region. Aromatic region lies from 909 to 667 per centimeter value. Next is infrared absorption process. So which molecule must absorb in IR region? It is also same as the other spectroscopic method, that energy absorption, or the molecules are excited to a higher energy from ground state to a higher energy by absorbing the infrared radiation. The absorption of infrared radiation is like the other absorption processes, is a quantized process. Molecule absorbs the radiation. The molecules, for example, any kind of the molecule absorbs the radiation, IR radiation, and per absorption it gets excited and excite into the higher energy level. The radiations in this energy range corresponding to the range encompassing the stretching and bending frequencies, vibrations of the bond in most covalent molecule. In the absorption process, those frequencies of infrared radiation that matches the natural vibration frequency. We know that any chemical bond, for example, this is a chemical bond, and that bond having bond is continuously vibrating. It's like a spring, so it continuously vibrating. It either stretching, bending, or any kind of the vibration. Now that vibration having the frequency, that a natural vibration frequency, we call it as a natural vibrational frequency. That natural vibration frequency, if the value of natural vibrational frequency is mu, if it is a mu, then the infrared radiation, if that mu is matches, means natural vibrational frequency is matches to the frequency of IR radiation, then and then this bond is able to absorb in the IR radiation, and that molecule absorbs, that bond absorbs the vibrational frequencies from the infrared radiations and increases the amplitude, means the amplitude before was like this, and after the absorption of IR radiation by that bond, the amplitude increases. So increasing amplitude shows the absorption in the IR frequency. So which kind of the bond will absorb in the IR region? Not all the bond get absorbed in the IR region, but the bond that must have the dipole moments, only those bonds that have a dipole moment that changes as a function of time are capable of absorbing the infrared radiation. So the dipole moment must be there. Dipole moment. So those bonds having the dipole moment that absorbs in the IR radiation. So the symmetric bonds such as those H2, Cl2, bond between the two H or bond between the two Cl, they do not carry the dipole moment, so they do not absorb in the IR region, and the bond must present an electric dipole moment is changing at the same frequency as incoming radiation for the energy to be transformed. The changing electrical dipole of the bond can then coupled with the changing electromagnetic field, the incoming radiation. The symmetric bond that has identical or nearly identical group on each end will not absorb in the infrared radiation. For example, the bond like, consider a symmetric bond, such a triple bond, the CH3 and CH3 attached. Now this triple bond is a symmetric, so the dipole moment is cancelled, so resultant dipole moment is 0 here. So such a bonds are not able to absorb in the IR region, even though they having the natural vibrations, or even though they carries the functional group. Or the another kind of example is a carbon-carbon double bond. Likewise, it is a symmetric compound and it is not able to absorb in the IR region. Next is why reason for use of wave number as a unit. We use the wave number as a unit. Main reason is that, as we know that energy is directly proportional to, or E energy is directly proportional to nu, that is wave number. So if we remove the proportionality sign, the energy is equal to h nu. H is the Planck's constant, and nu is equals to C upon lambda. C upon lambda, that is energy is equal to H into C upon lambda. So H and C are the constant. So energy is inversely proportional to the wavelength. So energy is inversely proportional to the wavelength. And energy is directly proportional to the wave number and frequency. So energy is directly proportional to the wave number and frequency. And that's why this is the main reason that chemists prefer to use the wave number as a unit, because energy is directly proportional. A higher wavelength corresponds to the higher energy. Thus, in terms of wave number, the vibrational infrared extend from the 4000 to the 400 per centimeter. Already we have seen the range from the IR spectroscopy, 4000 to 400 per centimeter in terms of the wave number. That is the main reason we use the wave number as the unit. Then frequency of vibration. So frequency of vibration is depends on the force constant. Frequency of vibration is depends on the force constant and the masses of the bond. Masses of the bond means what? The chemical bond is like a spring in between the two balls. Two balls means that atom bounded by a chemical bond. For example, this is one atom. It is bounded to the another atom. Likewise, now this bond is like a spring because it is continuously vibrating. So these masses means M1 is the mass of atom 1 and M2 is mass of atom 2, and bond is like a spring in between them. That bond is continuously vibrating. We will see later on the types of vibrations. So that bond is continuously vibrating, and the vibration, the kind of or amount of vibration is depends on the masses of that bounded atom. And according to the Hooke's law, according to the Hooke's law, the frequency of vibration is equal to 1 upon 2 pi c under root of force constant upon nu. So this is the frequency c of vibration. C is the velocity of light. Is it 3 into 10 raised to 10 centimeter per second? The frequency of light. Pi is a constant. Its value is 3.14. Then F is a force constant of bond. F is a force constant of bond, and rho is a reduced masses of atom, and it is denoted by M1 M2 upon M1 plus M2. So if we see the frequency of vibration is inversely proportional to the reduced mass of the atoms, while directly proportional to the force constant of bond. As stronger the bond, more frequency will require to vibrate, and as bulkier the atoms, bulkier the bounded atoms, then lesser will be the frequency of vibrations. So in this lecture we have complete the introductory part of the IR spectroscopy. In next lecture we will see the types of vibrations, stretching vibrations, bending vibrations, and then modes of vibration we will see in next lecture. Thank you. Till that time, please share, subscribe, and press the bell icon. So whenever I add the new video, you will get the notification. Thank you.